We have two broad classes of routing algorithms, link state and distance vector. We will first discuss distance vector algorithms. In distance vector algorithms, a router does not have a complete view of the network's connectivity and link costs. It starts with having only the cost of links directly connected to it. And by receiving cost information from its neighbors, it iteratively computes path costs to other nodes in the network. Therefore, the decision a router makes on the least cost path selection would depend only on the path cost information received from the neighbors. The routing is performed in an iterative distributed manner by the router. We will discuss Bellman-Ford algorithm as the representative of distance vector routing algorithms. In this algorithm, we compute the least cost path from X to Y as the minimum of cost path to Y through all direct neighbors of X. To compute this, we assume dx of Y shows cost of link cost path from X to Y. This is also called the element Y of distance vector of node X. Cost of a direct link from X to Y is given by cost of link X, Y. Given these notations, the Bellman-Ford equation says dx of Y, the element Y of the distance vector, is the minimum over all neighbors V of X, the cost of link from X to V, plus the cost of path from that neighbor V to Y. We compute this value for each of the neighbors on each update iteration and propagate the distance vector to all of its neighbors. Suppose we want to find a path from node U to node Z in the depicted network. The direct neighbors of node U are V, X, and W. So, node U starts by what it has, which is the link costs to its neighbors V, X, and W. That would be starting with cost of U and X of 1, cost of U and V of 2, and cost of U and W of 5. The next is updating the path cost in iterations of receiving the updates. Node U updates the path cost by receiving the cost path updates from these nodes, its neighbors, through the iterative process of calculating the Bellman-Ford equation on each update. Suppose we are at an iteration that these updates show dxz equals 3, dyz equals 5, and dwz equals 3. Using these pieces of information in the Bellman-Ford equation, duz will be the minimum of dxz plus cost of U and X, dyz plus cost of U and Y, and dwz plus cost of U and W, which is the minimum of 1 plus 3, 2 plus 5, and 5 plus 3. 1 plus 3, which is the path through neighbor X, is the minimum. Therefore, the next hop towards the path to Z will be chosen to be the node X. Note that no information about other links in the network is exchanged. For example, no updates about direct links from V to W, X to W, or W to Z ever provided to U. It is also important to note that those updates that you received also did not contain any information other than the cost of the path to destination from the neighboring node. Therefore, node U will record that the next hop to send packets to Z is X with cost 4. It does not have any knowledge of the path other than the next hop. The resulting forwarding table at node U will have the destinations in the network with the next hop or the first link to take to reach that destination. For example, to reach node X, the direct link U and X will be taken. To go to node V, the direct link UNV will be taken. To go to node Y, the next hop will be X, and the link UNX will be taken. To go to node W, again, the next hop will be X, and the link UNX will be taken. Same for node Z. The next hop will be X, and the link UNX will be taken. Node U does not have any other information about the availability or cost of the links in the network. Its view of the network is basically similar to what is being shown in the figure. Just knowing which hop to take, which link to go next to reach the destination.